Today I'll talk about black hole accretion that looks weird. And I'll explain why this black hole accretion is interesting and important to study. Why do we care about black hole accretion? In the context of supermassive black holes that I will use to illustrate that, for instance, in the case of the Perseus cluster, we have a black hole at the center that accretes gas and ejects gas and magnetic fields. And you can see by looking at this X-ray image on the left that was modified to show the small-scale structure. I apologize for the flickering. I think I have all the connections on my end. You see that the activity of the black hole launches waves and inflates cavities. And this is an important process known as black hole feedback that is crucial for galaxy formation and evolution. You can see more examples like this in the case of the M87 galaxy, where you see cavities blown out by the activity of the black hole, shocks, and other features. Finally, in this dramatic case of the galaxy cluster MS0735.6, we see two huge cavities inflated by the activity of the central black hole with the entire energy inferred to be contained within these cavities to be equal to the entire rotational energy of the central supermassive black hole. So there could be huge amounts of energy ejected by black holes. And it's important to understand the process of how black holes consume the gas and how they can inject part of this consumed energy in the form of the outflows. So when we look at this system, we don't really see small scales, what's happening very close to the black hole, and this is the case for most of the galaxies. So we tend to make the simplest approximations. That is, let's put a black hole at the center, let's put an accretion disk in the equatorial plane of the black hole, and let's see what happens. And what typically we find is that there are outflows along the rotational axis of the black hole, and the inflow is happening in the equatorial plane where we placed it. But in reality, the gas comes to the black hole from such large distances that it has no clue whether the black hole is spinning and which way the black hole rotational axis is pointing. It could be pointing vertically, it could be pointing horizontally. For all we know, the gas doesn't know. So if the relative orientation of the sense of rotation of the gas and of the black hole are randomly oriented relative to each other, typical situation will not be what I showed, but this one, where the typical angle of misalignment between the black hole midplane and the disk midplane is around 60 degrees. What will happen to the outflows? Will these outflows be there at all? Which way will they be pointing? Is an open question. Will they point along the black hole rotation axis, or will they turn around and follow the orientation of the accretion disk? And what will be the structure of the accretion disk? These are all open, very important, crucial questions for us to understand. So basic understanding of tilted accretion exists. What we think is happening if we have a puffed up disk that's tilted relative to the black hole, then this disk will be undergoing this intricate precession dance. So the disk will be dragged by the black hole spin, which drags the space-time, which then drags the disk, and the disk will be undergoing this precession similar to a tabletop. And in the case when the disk is thin, and this is perhaps the most interesting accretion state of black holes, the disks become thin because they radiate. And if they radiate brightly, we see them out to large distances. So this is the state that we think is happening in bright quasars. In this case, the situation is even less clear than in the case of a thick disk like that. Back 44 years ago, Barton and Peterson predicted that the inner parts of the accretion disk would align with the equatorial plane of the black hole, whereas the outer parts of the disk will be misaligned. The physics of this alignment is rather simple. If we were to break down this disk into individual rings, each ring will feel the rotation of space-time because black hole drags it around. And this dragging frequency drops off as a function of radius as roughly as radius to the -3rd power. So the rings near the black hole, if the disk is tilted, will precess at a much higher frequency than the rings at a large distance. And so if we start with a disk that was planar and tilted, and forgot about the interaction between these rings and let them evolve, then what we will find is that after a while, all of these orientations of the rings will be scrambled because the periods are different. And we would get a forest of these rings that, if we then switch on the viscosity in the disk, would average those angles out and lead to something that looks like it's an aligned disk. This process has been seen in hydrodynamical simulations of disks around black holes. But does this happen when we include magnetic fields, when we include the turbulence in the accretion disk, and when we accurately include the effects of general relativity? Because all of these effects of precession are purely general relativistic effects. So how difficult is it to include that? Well, it's pretty difficult. It's because the computational cost to simulate such a system scales as the aspect ratio of the disk, the thickness, divided by radius, to the -5th power. So if we want to consider this that is twice as thin, we'll have to invest 32 times more computational time. And part of this comes from increased resolution. But another very important part comes from the fact that thin disks take a long time to accrete and reach the central supermassive black hole. And the accretion time scales with various properties of the disk, like effective viscosity in the disk, the thickness of the disk, and the distance where we're interested in reaching the steady state. But if we pick typical numbers, then the accretion time scale is around 1,000,000 light crossing times of the black hole, which would be the longest general relativistic magnetohydrodynamic simulation ever. So clearly, it's very hard to run simulations that are high resolution and very long ones. So how can one possibly ever make it possible? Well, one approach that we just heard yesterday, John Hawley presented very nice work that showed that if you approximately include the frame dragging effect like I described, and if you evolve for a short fraction of the accretion timescale, you can find alignment of such tilted disks. But what if we want to try and solve the full problem? Is it even possible? Because this would require hundreds of millions of CPU core hours, which is maybe you can get in one PRAC allocation, only one simulation. What if we want to try and understand the physics and run a few of those? What is the approach then? Well, one way that we try to approach this problem is to try and take the general relativistic MHD code that we've been using. A number of groups has been using codes that are built on top of H-AMR and convert it to run on GPUs. So Matthew Lishka, who is presenting a poster here, he is graduating this fall from the University of Amsterdam and moving over as a postdoc to Harvard. He took this code and using a combination of CUDA and MPI and OpenMP, he got a 100 times speed up on a single GPU versus one single Blue Water CPU core. This is the speed that the code now attains in a single NVIDIA V100 or Titan V GPU. It's around 10 to the 8 zone cycles per second, which is the same speed as the non-relativistic codes as far as we know. So even though we include general relativistic effects, we're able to go as fast as non-relativistic codes, which don't have to take into account the general relativity. If we were to compare to how fast the code would go on Intel Skylake 4-core CPU, it would be 3 million zone cycles per second. If we were to buy enough of those, it would cost us $30,000 to get to the same speed as we could get on a $3,000 gaming-grade Titan V GPU. In addition to these speedups, Matthew implemented adaptive mesh refinement into the code, which is important when we study thin disks because the midplane can go and move through the grid. So we would like to be able to follow that. And you see the illustration of adaptive mesh refinement in action. Plus, different patches in the grid evolve at different time scales even at the same AMR level. So this adaptive time stepping helps us gain an additional speed up. This allows us to try and squeeze the most of the PRAC allocation blue waters. So for instance, 5 million GPU hour allocation blue waters effectively translates into 5 billion CPU core hours. And that is what allows us to try and attack the full problem. So how can we go about and doing that? Well, let's try first to run an accretion disk that would tilt by the angle of 45 degrees relative to the black hole spin axis, which is vertical in this movie. And the thickness of the disk that we will first try will be pretty thin, but not very thin. The thickness will be 0.05. So the ratio of the scale height to the distance to the black hole is 1/20th. And if we run with this simulation, we see that, well, first of all, you see that the disk is precessing. And in the vertical slice, like we're looking at, the disk is doing this dance. The left panel shows a zoom in on the right panel. And you can see, apart from precession, the disk is showing a bending wave mode, but it doesn't show any obvious signs of alignment with the equatorial plane. This is already a very expensive simulation with an effective resolution of about 3,000 times 1,000 times 1,000. It uses 3 adaptive mesh refinement levels. So let's try and go a little bit thinner and see whether this would be sufficient to find the alignment. So what we do here, I show the initial conditions. We actually start with a thick torus, and then we cool it to the target thickness. And when the movie starts, I will skip the burn-in period when the torus is cooling, and I will show you directly what happens. So the thickness here is about half of what you saw in the previous slide, 0.03, so 1/30th. So when you do that, you see that the accretion disk doesn't seem to show any alignment at all. So that is a huge disappointment. But then eventually, something happens, and the inner parts of the disk align. And you see not only do they align, they also break off from the outer disk. But then the alignment sometimes transiently comes in and goes away. We attribute this to the fact that the aspect ratio, even though it's already very small, the disk is very thin, it's not quite thin enough in order for the disk to be consistently achieve consistently the aligned state. So let's try and take a look at what happens if we look at an even thinner disk. So this is a disk that will be twice as thin as the one that you just saw. In fact, when you start this movie, we will start cooling the disk with an aspect ratio of 0.03 down to half of that. So initially, the alignment radius is around 5 gravitational radii, these unit sign gravitational radii. And as the disk gets accustomed to the new thickness, then this alignment radius keeps increasing and reaches around 10 gravitational radii. So the thinner the disk, the further out it aligns with the black hole. What would happen if we were to tilt the disk even more? This was 45 degrees. What if we tilt it at maybe 65 degrees? And then we see something really interesting. What is that? If we look at this in 3 dimensions, that you see that the outer disk, the outer big disk breaks up into 2, one of which seems to be doing its own precession. What we think is happening here is the inner disk could precess much faster because it doesn't have to involve the angular momentum that is concentrated at large distances. And so the inner disk is too impatient and precesses faster and outruns the outer disk and breaks off of it. So let's take a look at how it happens in the movie. So initially, we start with the disk that's tilted by 65 degrees. You see the inner part of the disk breaks off from the outer disk. And then that disk will, in turn, break into 2. The inner subdisk will get too impatient and will break off from the outer disk. And that process repeats. In the process, you can see that the jets run into the outer misaligned disk and completely vaporize it, which is really interesting for astrophysical purposes. When that happens, there'll probably be a lot of high energy emission involved. And you can also see that there are many more and more disks into which the original disk breaks into. And you can see that the jet tries to please every disk that it's interacting at a particular distance. So if you were to be able to see the jet on those small scales, you will see the jet changing its inclination angle as it tries to accommodate the different disks. Here you can see the disks finally merged because one precessed one time more than the other one. And now they're trying to separate again as the inner disk tries to outrun the outer disk. So far you cannot see in between. This presents itself as a warp. But then eventually, once the two disks cleanly separate, you will start seeing through to the central region again, which can lead to really interesting transient phenomena like change in look of AGN, where you see AGN transitioning from one type to the other, perhaps could be explained by these sorts of occultations by the precessing disks. I'm almost wrapping up over here. I wanted to highlight posters by 3 very bright young scientists who are presenting posters at the Blue Water Symposium. One is Matthew Lischka, who is currently a graduate student in Amsterdam and moving over to Harvard. He is presenting his work on the development of H-AMR and giving more details about the tilted disk physics that I just showed you here. Kaushik Chatterjee is also a graduate student. He's graduating a year after Matthew. So keep an eye out for him if you're interested in a computationally minded, very bright astrophysicist. He's going to be talking about the tilted images as viewed at the horizon scale by the Event Horizon Telescope. And Zach Endelman, he just graduated this Sunday from Evanston Township High School, and he's moving over to Yale College in the fall. He's presenting his work on the development of accretion disks in tidal disruption events. Let me wrap things up. We're very thankful to Blue Waters for enabling this qualitative leap in the physics of tilted black hole accretion disks. We now can simulate from first principles the alignment, breaking and tearing of tilted thin disks. And we are one step closer to try and bridge the gap between the theory and observations. We are extremely thankful to the Blue Waters team that kept running the machine perfectly, ensured that we can get the most out of our allocation, and helped us to create the 3D visualizations that you saw earlier. Thank you so much.